now let's see if we could derive this using kind of another perspective. So looking at specifically our elastic strain energy. So we previously defined our elastic strain energy as follows here. So our elastic strain energy in terms of our Young's modulus and strain. So, and then again, the elastic strain energy is a potential energy of our system. So we can rewrite and kind of say we reach this kind of same expression here, where our change in elastic strain energy is kind of the potential that we're working with. So we still have that same expression that we've been working with previously. So again, we could use our good old relationship, R naught and strain. So same thing as previously done. There's a couple of errors here. So I could rewrite my expression as follows. So please follow this one. So I could do the same, d strain, and then my change in my elastic strain energy, dr, and then dr, du, and let's see how we can relate those two. So if I do that, this is my good old friend again, the chain rule. So this expression becomes a little bit more complicated, and we can write it down though as follows. So after using the chain rule, applying the chain rule, I can get the following expression. So I get the following expression. So what I'm going to do d squared u, excuse me, let me write that a little bit clearer. D squared u, dr squared times, I'm going to do dr d epsilon squared plus du dr and then d squared r d epsilon squared. So that's applying our chain rule. Luckily, this expression gets much more, very simple. What's the second derivative of r with respect to strain? 0. So because we're linear r, we reduce to this expression. So I get my du, dr, and then dr, de is what? Dr, de, just going to be r naught. So we get this expression here. Again, we recover that same expression we just previously saw. So we know the atomic volume, again, is going to be equal to, again, for simple cubic materials, is going to be equal to this r naught. So again, simple cubic, we're pulling, so our atomic volume, this is our r naught. So our atomic volume is as such. And actually that's going to be kind of held. Our atomic volume, again, is your atomic distance. That's going to be held actually always. But anyways, so if we look at the, this is going to be our atomic volume. So our strain energy per unit volume is just going to be the energy per atom divided by our volume. So if we look at the energy per atom, it is this, so our potential, and then again, this is going to be Z as our number of nearest neighbors divided by 2. So that's the energy per atom. And the elastic strain energy, my total internal energy, essentially here, is going to be my energy of our atom at our stretch distance minus our equilibrium distance divided by our volume. So when we do that, divide out by volume. So again, we had an r squared here. If we divide out by, again, we're evaluating it at that r naught. So divide out by my volume, and then we get the following relationship. And again, one thing that kind of goes down here is the z over 2 actually. So it's the z over 2 r naught, that's z over 2 goes, and you get to get a little bit of an error right there. So once you have that, and that's your expression. So very similar. You see that the previous expression, we just had that 1 over r naught, but again, that's a constant. Material scientists, we're not too worried about that. But if you look at this energy per atom kind of argument, it could be a little bit more straightforward, a little bit more simple that you're working with. But yeah, that's all we've got here for. So this expression may be a little bit more palatable to what you're looking for. The key thing that we see in both these expressions is our Young's modulus is proportional to the curvature of our potential, divided out by some r naught value here. So that's the key kind of value that we are working with. So you can now start to plug in this and actually kind of start to calculate, and you'll do this in the problem set as well. So you'll see it's quite a bit off for most potentials that we work with, especially the Young's, the Leonard-Jones potential. But as you basically work with more complex potentials, especially embedded atom potentials, which take into account these more complex long-range interactions, you'll get closer. Now, We've always been working under a very, very, very kind of a simple assumption. What happens when the temperature changes? We've been working and actually assuming that we're basically close to, or we're working with a perfect crystal. So how do those atoms, how is our Young's modulus going to change essentially as we kind of expand our material, or as we kind of change? So we're going to get into that next time. What is the origin of our favorite parameter of thermal expansion coefficient alpha? All right, see you next time. Thanks. Bye.